Level 0. A storm is 20 kilometers away and somehow you already know it's there. Not from the sky, not from the wind, from a sound so deep and distant that your body seems to register it before your mind catches up. That isn't an accident. It's physics. Lightning superheats the air around it to roughly 30,000 degrees Celsius, 5 times hotter than the visible surface of the sun, reached in roughly 1 millisecond inside a channel only a few centimeters wide. The air explodes outward as a shockwave. That shockwave is thunder. What makes it rumble is geometry. A bolt can span 2 to 3 kilometers from top to ground. Every section of that channel contributes to the shockwave reaching your ears at a slightly different time, stretching one event into several rolling seconds of sound. The rumble is not one thing. It is the same event arriving in pieces, each piece from a different part of the bolt, each slightly delayed by distance. When a strike lands within roughly 100 meters, those layers collapse into a single crack that people nearby describe as something that happened to them, rather than something they heard. The shockwave at that range is carrying enough pressure that it interacts with the body directly, felt in the chest and sinuses before the brain has finished processing it as sound. The distinction between hearing thunder and being hit by it begins to blur. Thunder fades within a few tens of kilometers. Lightning is visible from 160 kilometers away. The storm can exist far beyond the reach of its own sound. What people call heat lightning is an ordinary storm at that distance, its thunder never arriving. The lightning is real. The silence around it is just a matter of how far sound travels compared to light. Thunder itself is always the same basic phenomenon, a shockwave created when lightning rapidly heats and expands its surrounding medium. What changes is the lightning that creates it, where that lightning occurs, and what the shockwave has to travel through. But what happens when the lightning doesn't fall toward the ground at all? What if it starts there and climbs upward? Level 1. Most people picture lightning as something that falls. Cloud charges, ground charges. A bolt bridges the gap downward. That is one way it works. Upward lightning initiates from tall structures such as skyscrapers, broadcast towers, and wind turbines, traveling upward toward the cloud base. No downward leader from the cloud triggers it. The electric field concentrates at the tip until a leader launches upward on its own. It is the structure reaching toward the storm rather than the storm reaching toward the structure. And that distinction alone inverts the entire picture most people carry of how lightning works. A major broadcast tower in an active thunderstorm is not a passive target. It can generate upward lightning repeatedly during a single storm, initiating each discharge rather than receiving it. The systematic study of upward lightning from tall structures has been conducted extensively in places like Switzerland and Japan, where instrumented towers and exposed terrain provided researchers with controlled conditions to observe and measure it directly. The behavior turned out to be far more common than anyone had assumed. Upward lightning produces the same basic shockwave as any other strike, so the thunder itself is not fundamentally different. What changes is the direction of the discharge. Lightning isn't something that simply falls from the sky. It forms wherever the electrical conditions allow a discharge to develop, and tall conductive structures alter those conditions at their tips in a very specific way. The lightning can go up. It can also stay entirely inside the cloud, and when it does, the thunder can lose the clear point of origin a ground strike gives it. Instead of coming from somewhere, it can seem to come from everywhere. Level 2. Most lightning never reaches the ground. Estimates commonly put the share at around 75%, though the exact figure depends on how lightning is classified and measured. What that majority produces is intracloud lightning, discharging horizontally between regions of opposite charge within the same cloud, and most of the electrical activity in any thunderstorm is happening up there, invisible from below. A horizontal channel extending tens of kilometers through the cloud sends its shockwave downward across a wide plain simultaneously. The result is a diffuse, prolonged growl with no obvious point of origin, because acoustically, it does not have one. People standing beneath a storm heavy with intracloud activity often describe the thunder as surrounding them, rather than approaching from any particular direction. That is an accurate description of what physics produces. Thunder also contains substantial low-frequency energy, including frequencies below 20 Hz, below the normal range of human hearing. Those frequencies travel through the atmosphere as real pressure variations beyond the range at which audible thunder fades. A storm can be generating these pressure waves continuously, while the sky above appears silent and unremarkable. The sound is there, it is simply operating outside the register the human ear was built to detect. There are documented instances of thunder without visible lightning, a clear rumble from a sky showing no discharge. The explanation is intracloud lightning fully concealed within dense clouds, generating shockwaves that reach the surface with nothing visible to account for them. Sound without light. The sky gives you the consequence without showing you the cause, And the effect on the person hearing it, a rumble from a cloudless or featureless patch of sky, is difficult to rationalize in the moment. Now move the storm into conditions where the snow itself becomes part of the equation. Level 3. Snow absorbs sound. A fresh snowfall muffles the world in a way that most people recognize immediately. Thunder inside a snowstorm sits against that association as something categorically mismatched. Thundersnow is real and documented, and the interesting part is not the lightning. It is what the snow does to the thunder afterward. For thundersnow to occur, the atmosphere must be cold enough to produce snow and unstable enough to sustain the vertical updrafts that drive lightning. That combination is uncommon, which is why thundersnow is rare enough that many people never encounter it. When it does happen, the storm looks from the outside like any other winter snowfall. Nothing about its appearance communicates the electrical activity happening inside it. The flash of lightning through dense snowfall is often diffuse rather than distinct, scattered by the falling crystals into a brief, sourceless brightening rather than a clear bolt. In a snowstorm, atmospheric conditions can strongly affect how far thunder travels, while the falling snow adds additional scattering and absorption. The result can be a storm whose thunder is heard over a surprisingly short distance. The warning range that thunder normally provides is compressed, a storm that looks and sounds quieter than it is. From here, the escalation leaves atmospheric moisture entirely. The next energy source is geological. Level 4. A volcanic eruption column can reach 20 kilometers into the atmosphere. Inside it, billions of ash particles, rock fragments, and glass shards collide continuously as they are driven upward. Those collisions help separate electrical charge through particle interactions, creating the conditions for volcanic lightning, the same outcome as a storm cloud, but driven by geology rather than weather. What makes volcanic lightning unusual is not just where it happens, but when. Researchers using high-speed cameras have documented lightning discharging within meters of the volcanic vent, in some cases before the erupting material has even fully separated from the crater rim. The charge separation can happen that fast, inside the most violent part of the eruption itself. The result is volcanic lightning, arriving against an acoustic backdrop weather systems cannot produce. The eruption column is already generating continuous low-frequency sound from the mechanical force of the eruption itself. Volcanic thunder does not emerge from silence. It arrives against an ongoing deep frequency output, registering as a sharper intrusion into an environment that was already overwhelming. Observers near large eruptions have described the effect as a crack, appearing inside a roar, two sounds that belong to different phenomena, arriving at the same time from the same direction. During the 2022 eruption of Hunga Tonga, the electrical activity during the eruption column's formation was among the most intense ever recorded from a volcanic event. The eruption produced lightning and thunder locally, while its much larger atmospheric pressure wave traveled around the planet multiple times, detectable on instruments worldwide. The thunder was local. The pressure wave was planetary. Two disturbances from the same eruption, operating on completely different scales. The lightning and its thunder behaved exactly as expected for a large volcanic event. The pressure wave behaved in a way that still generates research papers. The next level does not just produce thunder as a byproduct, it produces an entire thunderstorm as a byproduct. Level 5. When a wildfire grows large enough and hot enough, it stops being simply a fire. It begins generating its own weather. The mechanism behind this is the same one that drives any convective storm. Heat rises, rising air cools, moisture condenses. The difference is that a wildfire's heat output can be extreme enough to drive this process far higher and faster than solar heating alone ever would, punching a column of smoke-laden air into the upper atmosphere and triggering the electrical dynamics that follow. A pyrocumulonimbus cloud forms when a wildfire drives a convective column of superheated air and smoke high enough to initiate thunderstorm dynamics. Charge separation begins inside smoke, ash, and carbonized particles. A fully developed pyrocumulonimbus produces real lightning above an active fire and fires it back down into the fire zone. A wildfire generating its own electrical storm uses that storm to spread itself. Lightning strikes outside the controlled perimeter set new fires. The fire builds a mechanism and deploys it. What makes this particularly difficult for fire crews is that the new ignitions appear outside the area being actively managed, started by a storm the fire itself produced, operating above the reach of anyone on the ground. The 2019 to 2020 Australian wildfire season produced multiple confirmed pyrocumulonimbus events, some reaching cloud tops above 16 kilometers. Smoke entered the stratosphere and remained detectable globally for months afterward. Thunderclaps in areas no observer could safely reach. Thunder from a storm the fire made, above a fire the thunder was helping to expand. People who have reported hearing pyrocumulonimbus thunder from safe distances describe it as arriving against the background roar of the fire itself, indistinguishable at first from the general noise of the event, recognizable only when a distinctive sharp crack cuts through the sustained low frequency of the burning below it. That is the upper end of what heat and smoke can build. The next level reaches the upper end of what Earth's electrical system itself can generate. Level 6. Not all lightning carries the same energy. At the far extreme of that range sit events researchers call superbolts, lightning of exceptional output, substantially exceeding typical strikes. Precise thresholds differ between studies, but the consistent finding is that superbolts sit far enough from the ordinary distribution to be treated as distinct. They were first identified through satellite-based lightning detection in the 1970s. Initial measurements were questioned. The instruments were working correctly. What makes the geographic concentration particularly puzzling is that oceanic winter storms are not typically the most electrically active storms on the planet. Continental summer thunderstorms, particularly in tropical regions, produce far more lightning in raw terms. The fact that the most energetic individual discharges cluster preferentially over cold winter ocean is something the research has not yet satisfactorily explained. It suggests that raw lightning frequency and peak discharge energy are measuring something fundamentally different about storm physics. What separates a superbolt isn't merely that it is loud. Its electrical output can be dramatically greater than that of an ordinary lightning discharge, pushing the atmosphere toward the extreme end of what Earth's storms can produce. Their geographic pattern remains genuinely unresolved. Superbolts occur disproportionately over the ocean, concentrated over the northeast Atlantic and the Mediterranean during winter months, while continental summer thunderstorms, which dominate raw lightning frequency, are underrepresented. The leading hypothesis involves structural differences in how winter oceanic storm systems distribute charge, but the mechanism is not settled. The pattern was identified decades ago, and it remains one of the more quietly persistent open questions in atmospheric science. Superbolts push the energy of an atmospheric electrical discharge far beyond what an ordinary strike produces. That is the ceiling on what a single discharge can produce. But a single discharge is still one event, one channel, one crack. What happens when the storm itself stops being a single event and becomes something closer to a system, organized, self-sustaining, and moving faster than most people drive? Level 7. Most thunderstorms are local events. They form, discharge, and collapse. A derecho stretches that entire cycle across an entirely different scale. A derecho is a long-lived, fast-moving line of severe thunderstorms, driven forward by its own outflow. Where an isolated storm cell might cover a few tens of kilometers and exhaust itself in an hour, a derecho can maintain its structure over vast distances and last well into the following day. It is not one storm. It is a system, a convective line that regenerates as it moves, continuously replacing the cells that collapse at its rear with new ones forming at its leading edge. The thunder that a derecho produces is different not because the physics of thunder change, but because the lightning producing it is spread across an enormous, continuously moving system. Observers in its path have described hearing overlapping thunder for extended periods as the convective line sweeps through, each discharge arriving from a slightly different position along the line, so that the sound has no clear beginning or end from any fixed point on the ground. The storm does not arrive and leaves. It arrives and continues arriving, cell by cell, until the system has moved entirely beyond range. What distinguishes derecho thunder acoustically is its apparent directionality. An isolated thunderstorm gives you a single advancing source. A derecho, with its convective line stretching across the full arc of the sky, produces lightning from multiple simultaneous positions. Because the sources are distributed rather than concentrated, the thunder seems to come from along the storm rather than from it, a moving wall of acoustic events rather than a discrete passing cell. The 2012 North American derecho tracked from Illinois to the mid-Atlantic coast over roughly 12 hours, covering more than 1,000 kilometers. Wind gusts exceeded 130 kilometers per hour across multiple states. Thunder accompanied the lightning along the line, with different cells producing different discharges as the system crossed the continent. A single thunderstorm is an event with edges. A derecho is a system with a front. The thunder it produces is not a consequence you wait out. It is a property of something continental in scale, organized, fast-moving, and self-sustaining. The same storm physics that produces a single isolated crack here produces something closer to a sustained acoustic presence when operating at that scale simultaneously. What you are hearing is not one storm passing. It is a system moving through, replacing itself as it goes, producing thunder from a different cell every few seconds for as long as it takes to cross whatever is in its path.